Hi everyone, welcome to the second video on chapter 13 electrochemistry. Right, so in this video we are looking at part 2 of the notes, whereby we are actually going to zoom into the electrolysis of aqueous solutions of compounds. Right, so in the previous video you were introduced to the idea of electrolysis. That means to use electricity to actually break down ionic compounds to the various products, and we were focusing on the molten ionic compounds. Right, molten means that they are in a liquid state. In this video, we are going to focus about the aqueous solutions, and as you recall from what I mentioned in class, this will form the bulk of the concepts for this entire chapter. Right, so let's get started. So by the end of this video, only one key objective, and that is you must be very confident to predict the products of the electrolysis of an aqueous electrolyte using the idea of what we call selective discharge of ions. Now, in a molten substance, right, that we saw earlier, there is always only one cation and one anion. However, when you have an aqueous solution, this time round, it may contain more than one type of cation or anion in the electrolyte. So, what do I mean by that? To all students here, I would like you to take note that when you have an aqueous solution, what is different now is that there is now the H plus ion as well as the OH minus ion that will be present. Now, previously, when you look at the ionic compound, we were focusing only on the cations and anions of the ionic compound. In this case, because it's an aqueous solution, we are looking at aqueous sodium ion as well as aqueous chloride ion. But this time round, there are also your H plus and OH minus ions. Now, this actually came from H2O. Okay, we will not go in depth into what it means, how come H2O can result in this, but if you're curious about it, you can go and search about this concept called partial dissociation of water, right? So take note now that there is actually some new ions here, which will actually affect how our analysis of the question will look like. So because there may be now more than one type of cations or anions, the discharge of the ion is now a selective process. Now, what do I mean by selective? I mentioned just now that there can be H plus, there can be Na plus, there can be OH minus, there can be Cl minus. If you recall in the previous video, this will mean that the ions will move towards the electrode, and then there is actually a choice between which ion should be reacting. So that is what we call the selective discharge of ions. This depends on a few factors. Number one, if you are looking at cations, right, the cations which are at the cathode, the selective discharge is actually dependent on the reactivity series. This is what you learn in the metal reactivity series chapter. If you are looking at the anions, which happen to be at the anode, this selective discharge of anions also depends on certain factors, which we'll take a look at over the next few slides. Last, based on anions, there is also a need to consider the effect of concentration on the selective discharge of anions. Let's take a look at each of these factors and see how they affect the selective discharge of ions. First, on the selective discharge of cations. Now, we all know that cations has a way of being reduced at the cathode, right? So what this page is trying to show you is that there's actually a trend, and this trend is that it actually gets easier to discharge the ion if you are looking at silver, copper, hydrogen, etc., as compared to at the top here, whereby you have potassium, sodium, calcium, magnesium, etc. Now, you will recall in the previous lesson that, the previous chapter, that the more reactive the metal, the greater its tendency to form ions. So, for instance, potassium, sodium, calcium, and magnesium, they are very reactive and they will form ions very easily. This will also mean that the chances of the ion actually being discharged, which means that the ions actually wants to form back to the element, actually the likelihood of it actually increases down the reactivity series. Now, what do I mean by this whole thing? Basically, what I'm trying to say is that because potassium forms potassium ions very readily, what we can tell is that the potassium ions are actually more stable. Because potassium, more reactive, when they form the ions are very, very stable. Silver, on the other hand, we know that silver metal is not very reactive. This means that it is, in a way, the least stable or less stable over here. In chemistry, when something is less stable, it will mean that it's more reactive. When it's more reactive, means that if given a choice, the ions at the bottom part in this whole series that you see over here will actually want to react. So what this will mean is that if you are given hydrogen ions, if you are given copper ions, in this case as an example over here, the discharge of hydrogen ion will look like this half equation here, whereby 2H plus in aqueous plus 2 electron form hydrogen gas. The discharge of copper 2 ions will look like this equation over here, whereby copper 2 plus aqueous plus 2 electron give you copper solid. Now, when you look at this entire series, you will know that the one that's at the bottom of the series is more easily discharged. So based on this thing, what we can conclude is that Cu2 plus is preferentially discharged as compared to H plus. This will mean that if there is both H plus and Cu2 plus present, the Cu2 plus will actually go and react first. Reason is because over bottom here, these are the least stable. Least stable means they are very reactive. The one at the top here are the most stable, means that they're not reactive. Remember that we are talking about ions. Okay, so don't confuse this with what you learned in the previous chapter on reactivity series. Over here, I'm talking about the ions. I'm not talking about the metals. That means I'm not saying that potassium, sodium, calcium matters. I'm looking at the ions. Right, so this is the first factor, selective discharge of cations based on the reactivity series. The second factor will be looking at anions, right, which are at the anode side. Right, so anions that will never be discharged no matter what's the condition are sulfate and nitrates. So as long as you see sulfate and nitrate, you don't need to think too much about them. They will just stay there. They will not react. And in that case, usually the one that is reacting in the whole setup will be your hydroxide anions. Right, so your hydroxide anions, in terms of the discharge, it will look like this, whereby they actually form water and they form oxygen. Right, and in the process, there's actually a loss of 4 electrons. So in case you're not too sure why 4 electrons, over here is 4 of the OH minus. Right, so 4 minus on the right hand side, then also must be the 4 of the electron minus. That this shows that the charge is actually balanced on both sides. So this is what happens if you have sulfate versus OH minus. So this part of the notes is trying to tell you that if you have sulfate versus OH minus, or if you have nitrate versus OH minus, what will be discharged will be your preferred OH minus, OH minus. The sulfate and nitrate will not react. This is what factor 2 is trying to tell us. Next, when we go on to factor 3, factor 3 actually says that, hey, if now you happen to have a higher concentration of a certain anion, this time round, there is a chance that the anion will be discharged. Right, and this is usually, in terms of our syllabus, right, we focus a lot on chloride. So when there's a high concentration of chloride ions, there's a chance of the chloride being discharged as compared to hydroxide ions. Don't worry so much about these 3 rules. We're going to go through 3 examples in this video. Take a look at how they are being explained, and then hopefully you see how the 3 rules actually come together, so that the 3 factors actually come together to help us decide what's happening. Right, so with these 3 factors, let us take a look at when we are given a question, what is the step-by-step method to do? There are 4 steps that we need to think of. Number 1, just like what we did in the previous video, you first find out what's the cations and anions first. Number 2, decide where the anions will move, decide where the cations will move, and then whether they will be reacting, which one will be reacting. Okay, so that's step number 2 and 3 actually. Step number 4, the one that doesn't react will stay behind, and if they stay behind, they will form certain things within the electrolyte, and that will affect how the whole reaction looks like. So 4 steps, and we are going to apply it first to the next page of the setup. Right, so if you look at your next page of the notes, right, you realize that it's drawn for you the same diagram of your electrolytic cell. Okay, you'll look very different from what you see on the slides, but take note of where the positive and negative electrodes are, then we'll draw it accordingly to show where the ions are. Okay, so let's get started first. This first example that we're going to look at is the electrolysis of what we call dilute sodium chloride solution. Right, so inside dilute sodium chloride solution, there are 4 different ions. Here, it's no longer sodium and chloride only, because there's also the H plus and OH minus, which came from the H2O. And if you take a look at them, all of them are in aqueous state because this whole thing is aqueous. Alright? The setup will look like what you see on the right hand side, whereby there is still a battery. Based on this diagram that I have over here, this side is a negative, this side is a positive. Right? So as students, when you look at this thing, you must remind yourself, inside the whole setup, there's so many ions, right? Where will the ions go? Because there's a positive one, the one that comes to a positive one will be your Cl minus. The one that comes to a positive one will be your OH minus. Right? These are your anions will come to the positive side. The one that goes to the negative side one will be your H plus ions and your Na plus ions. Right? Now that you have this setup, it will mean that you need to choose who is going to react. That's why this whole video is about selective discharge. Right? So we're going to take a look at it step by step and see which is the ions that get discharged. First, let's zoom into the anode. Right? Which one is the anode? The anode is this one that is positively charged over here in this diagram. Same thing on your own notes, right? Go and label the drawing as well. Right? So anode is this part. And at the anode, what happened is that, like what I mentioned just now, the hydroxide ions, the chloride ions will come around the anode because they are negatively charged. They get attracted to a positive electrode. Once they are there, we look at the factors, the three factors. If it's anions, we look at factor 2 and factor 3. Factor 2 says that usually hydroxide ions will be preferentially discharged. And in this case, the hydroxide ions will react, you'll form water and oxygen as shown in this half equation. As a student, when you look at this thing, you will realize that there will be effervescence happening because you are forming oxygen gas. So bubbles will start to form, and then you'll form the airspace at the top of the test tube that you see in this slide. Right? So colorless effervescence will be formed, and then your chloride ions will stay behind in the solution because they don't get reacted. So over time, the OH minus will start to disappear until there's no more OH minus. Then the reaction is kind of done, right? But you're just left with a lot of the chloride. So that's what happens at the anode. Remember, anode is where we have oxidation. And ox, red cat. Right? So this is an oxidation that you're looking at. At the cathode, right? At the cathode, like what I mentioned just now, this is where your cations come, right? So your Na plus will come here, and there's also a H plus from water will come over here. So this time around, we also need to know what is a selective discharge, right? So if you recall in the reactivity series, right, we had your please stop calling me blah blah blah, all these things, right? And if you remember what I mentioned just now, sodium ion is here, hydrogen ion is here. We know that in between there's a lot. Okay, we are looking at ions, we're not looking at metals. And you should remember that just like I mentioned that the one that's at the top is actually the more stable ion. The one that's at the bottom is actually the less stable ion. Right? And because the less stable ion, H plus ions will now be preferentially discharged to form hydrogen gas. This is how the reaction will look like. And similarly, you will see effervescence. So a lot of bubbles form. You'll see the air column at the top. Then the hydrogen gas will be gathering there. And over time, all the hydrogen ions will be used up. And you're left with your sodium ions remaining in the solution. So this is what happens at the cathode. Now, when you put everything together, in summary, the overall reaction is actually 2H2O becoming H2 plus O2. Basically, if you sum up the entire process, you realize that, hey, actually this is just electrolyzing the water. Right? So although I said sodium chloride solution at the start, basically it was only the water that was reacting. What happened to the sodium chloride? They stay behind. Because they stay behind, it actually becomes more and more concentrated as the amount of water actually decreases. So this is what happens if you have what we call a dilute sodium chloride solution. You realize that when it comes to solution or aqueous, whether it is diluted or whether it is concentrated, the concept will be quite different. So read the question carefully to know whether you're looking at a diluted one or concentrated one. What if today the question is a concentrated one? Now, when it's a concentrated one, similarly, the ions will still be the same. Sodium, chloride, H plus, and OH minus. Of course, this comes from the water. Everything is in aqueous state, right? Aqueous state. But the trick now is that because the concentration changes, if you recall in the second page of these notes, there is factor number 3. Concentration can also affect how anions are reacting, right? So we are going to explore this over the next few slides. But first, let's take a look at a video of the setup of electrolysis of sodium chloride solution.
Sodium chloride is one of the world's cheapest and most widely available raw materials. It's found as rock salt in vast deposits underground, and it's dissolved in all the oceans of the world. The electrolysis of sodium chloride solution is an important industrial process. Mix the salt with water, pass an electric current through it, and a variety of useful substances are produced. To work out what's going on, here's a much simpler setup in the lab. Two electrodes immersed in sodium chloride solution are connected to a power supply. The electrodes are made of carbon. They're supported by an insulated hook. See what happens when an electric current is passed through the solution. What evidence is there that chemical reactions are taking place? Bubbles appear around both electrodes, a sign that gases are being produced. To collect the gases, a test tube full of sodium chloride solution is placed over each electrode. Gas displaces the solution and collects in the top of the tube. So, what are the gases? Both are either very pale or colourless, but they can be identified by simple tests. The gas collecting at the positive electrode is tested with damp blue litmus paper. It goes red and quickly bleaches white. The gas is chlorine. The gas collecting at the negative is tested with a lit splint. It pops, a sure sign that this gas is hydrogen. So, why does the electrolysis of sodium chloride solution produce hydrogen and chlorine? Imagine you can see the charged particles in solution. There are sodium ions, which are positive, and chloride ions, which are negative. The others are present in water, positive hydrogen ions and negative hydroxide ions. These different charged particles are all free to move. Once the power supply is switched on, the positive ions are attracted to the negative electrode. The negative ions move towards the positive. Sodium and hydrogen compete to gain electrons. The hydrogen ions win out. They lose their positive charge and form bubbles of hydrogen gas. Competition also happens at the positive electrode. This time, chloride ions win out, losing their negative charge and forming bubbles of chlorine gas. Industrially, the electrolysis of sodium chloride solution can provide us with many useful materials. Chlorine is used as a disinfectant in swimming pools. Hydrogen is used as rocket fuel. And the sodium hydroxide solution left behind is used in the manufacture of bleach.
Alright, so as you can see from the video, you will realize that he looks quite different from what I was explaining in the earlier part of this video, right? Because their product was chlorine gas instead of oxygen gas. Now that is because in this setup, they were using concentrated NaCl, right? And we're going to take a look at what is the difference compared to what we have seen in the previous part that I've mentioned earlier about diluted NaCl. Now, when it's a concentrated NaCl solution, similarly, as per what we have mentioned, you will have your ions move towards the anode. Your anions will move towards the anode, so you have your hydroxide as well as your chloride. But because now you are dealing with a concentrated sodium chloride solution, you mean that there will be a lot of the chloride ions over here. Now this actually causes factor 3 to come in, whereby this time round, the chloride ions will now be preferentially discharged to form chlorine gas. So we know that chloride ions, when they are being discharged, in this case 2Cl- will form Cl2 gas plus 2 electrons. This is the part that gets interesting, because just now I was talking about hydroxide ions getting discharged. But because there is a difference now where you're using a concentrated solution, the anions, in this case the chloride, will be the one discharging instead of the hydroxide already. Right, so this is one key difference to take note of. Read the question, take note whether is it concentrated or diluted. So what will you see? Chlorine gas is a yellowish green gas, so it is a yellowish green effervescence that will be forming at the anode. At the cathode, like what we saw just now, H plus and Na plus will come towards the cathode. Since it's concentrated, naturally you expect more Na plus to be there. However, at the cathode, if you just look at factor 1 on page 2 of these notes, there is actually no effect of concentration. You will still be H plus ion being discharged. That means at the cathode, concentration does not matter. Concentration only matters for the anode part, right? So take note of this whole process. So over here, your hydrogen ions will be reduced to form hydrogen gas, and you'll still see your colorless effervescence, and your Na plus ions will still remain in the solution. So over some time, you'll realize that in this setup now is very different in the reaction, because it was actually H plus and Cl minus that are reacting. So if you recall just on the equation, right, there was actually 2 Cl minus becoming Cl2 plus 2 electron. There's also a 2H plus 2 electron becoming H2. So what actually happened in this entire reaction was the chloride and the H plus are the one reacting, and it forms chlorine gas and hydrogen gas. So this is actually how the overall equation looks like. 2HCl actually is forming Cl2 and H2. Resulting solution will mean that it's made of what is left behind. The leftover will be hydroxide and Na plus. And when you have hydroxide and Na plus left behind, right, this will mean that they will actually form NaOH. Right? NaOH, we all know that it's an aqueous, it's an alkaline chemical because it can be associated to form hydroxide ions. So overall, the solution actually becomes more alkaline. Interesting thing is that if let's say you do this experiment and you put a universal indicator, you actually can see the solution start to turn color over time. Alright, so we are going to try this out when we are in school during the lab session to play around with the electrolysis of sodium chloride solution, both the diluted and the concentrated version. Then we'll see how it actually looks like. Alright, so that will cover the second setup that we see. Now, the last one, before we go on to self-practice for this entire part 2 of the notes, let's just apply this entire thing to look at a different chemical now. Let's say we look at aqueous copper 2 sulfate solution, right? Using unreactive electrode. So inside an aqueous solution of copper 2 sulfate, what are the ions that's present? I hope you can recall. Aqueous means that there must be H plus and OH minus. Copper 2 sulfate means that is Cu2 plus and SO42 minus. Just look at the ions. There's no need to come up with new ions yourself. Similarly, we know that in the setup, there will be different electrodes and ions will move. So let's take a look at this video and see how it might look like. So in this video, you'll realize that there is 2 electrodes. I think these are all graphite or carbon. Then over time, if you look at the reaction, you realize that one of the electrodes, there's actually bubbles if you zoom in and look at it closely, whereas the other electrode actually starts to have this reddish brown thing that's forming. Okay, this is actually what it looks like when you're doing electrolysis of copper 2 sulfate. Let's take a look at this video again. Alright, as you can see from this video, when the electrode went into the solution and the electricity is run through, right, one of the electrode actually had effervescence, the other electrode actually had this reddish brown solid forming over here. I'm sure most of you will know now that this reddish brown solid must be copper, right, because there's copper ions inside. But let's take a look at the whole setup and ask ourselves, how do the ions actually move again? So, at the anode, right, so which one is the anode? If you look at the terminal of the electrode, this one is positive, this one is negative, right? So we know that in terms of the ions, right, the OH minus, okay, sorry for the color choice, OH minus and SO4 2 minus will actually come towards the positive electrode because they are negatively charged, right? So they'll move towards there. And what happens to negative ions? They will be oxidized, and ox, red cat, right? So at the anode is where you have oxidation. So now you have two choices, hydroxide or sulfate. If you go to the second page of this set of notes, you know that factor 2 says that, hey, if you have sulfate, sulfate will actually remain as an ion. That will mean that hydroxide will be the one that's preferentially discharged. And I hope by now you can try to practice writing out the half equation yourself. Okay, it's good to always practice and get familiar with the way the equation is being written down. And that means you should see that there will be effervescence observed over here. So just now, the electrode that you saw the bubbles, that must be the anode whereby the oxygen gas is coming out as bubbles, right? So that is what happened just now. At the cathode, right? At the cathode, because of the ions that's over there, so in this case, at the cathode you have your Cu2 plus and you have your H plus that will be over there. Cu2 plus and H plus will be moving towards the cathode. Now we think about which one will be selectively discharged. If you recall the reactivity series that we saw just now under factor 1, in terms of ions, we know that there's sodium all the way to the top, then you have your H plus, followed by Cu2 plus, followed by silver, followed by gold, etc. And if you recall, the one at the bottom is the least stable. The one at the top is the most stable. So between H and H plus and Cu2 plus, actually Cu2 plus will be preferentially discharged to form copper metal because it's more at the bottom of the whole series, right? So it will actually react, copper 2 plus, aqueous will actually plus 2 electron, and you form copper solid, which is a reddish brown deposit. Over time, the H plus will stay behind in the solution. So if you look at this entire thing, right, you realize that at the anode, what happened was that the hydroxide gets discharged because sulfate, based on factor 2, can never be discharged. At the cathode, copper 2 plus is discharged because, based on the reactivity series, which is factor 1, we know that copper 2 plus is less stable, it will react. H plus will choose to stay as H plus in this case. So overall, what actually happens was copper ion as well as hydroxide ions were being discharged and they form copper metal as well as oxygen in the process. So copper will be forming on the cathode, that's why just now in the video you saw the reddish brown solid. Oxygen will be forming at the anode, that's why you saw the effervescence. Over time, the blue color of the solution becomes lighter. Why? Because there will be less of the Cu2 plus ion because they are being discharged to form copper metal. So the blue color which comes from the copper 2 plus ion actually gets less and less and less. In addition, we know that at the end, sulfuric acid will be formed because H plus and sulfate ions stay behind. So when they stay behind, they actually form your H2SO4. And therefore, overall the equation will actually become overall the reaction will actually form this acidic sulfuric acid at the end. So this is actually what happens in the whole process. Okay, so this will take some time. It requires a bit more practice and we will try this out using our 10S series and the other questions practice that we may have. Okay, so now the last part of this video is a self-practice. Now this self-practice is to look at the electrolysis of water. Right, if you recall in the part 1 video, which I won't show again, there was this video that shows you the electrolysis of water whereby there's effervescence happening. Okay, so in reality, when we do electrolysis of water, we kind of cheat a little by adding dilute sulfuric acid in. Okay, think about why do we need to do this step. Okay, but this will actually allow for the reaction to happen more quickly and also to ensure that you can really observe for the effervescence that's happening on both ends. Okay, so think about why this step is necessary. Okay, so electrolysis of water. Water I mentioned just now, just like the aqueous solution, right? That means inside there's H plus and there's OH minus ions. Right, so now the question to you is that where will the ions move and what will be the product that's forming? Okay, so you may wish to pause the video at this point now because in the next 5 seconds or so, we are going to take a look at the step-by-step explanation of the self-practice question. Alright, let's now take a look at the self-practice on electrolysis of water with inert electrodes. Now, we know that in water, right, like what I mentioned earlier, the anions will be OH minus and the cation will be H plus. So in this entire setup, we can also label the electrode based on the charge of the battery, and we can deduce that over here there will be hydroxide ions, and over here there will be H plus ions, because the opposite charge actually attract each other. The good thing over here is that there's nothing much to compare, because you cannot you have no choice. There's only one reaction that can happen, right? So the anode, which is where the hydroxide ions are, and the cathode where the hydrogen ions are, that will be where the reaction will take place, right? So in terms of the reaction, we will just keep A first and just zoom into B, right? So at each electrode, let's talk about anode first. And the anode is where you have your OH minus ions. So what exactly happen over here is oxidation of OH minus ions actually take place. So the equation will be for OH minus, if you recall from the previous question that we did, you form 2H2O liquid, you form O2 gas, and you form 4 electrons. At the cathode, an ox red cat. So this is where reduction of your H plus will happen, and therefore we have our 2H plus in aqueous form actually forming H2 gas, and in the process what happens is that they actually gain 2 electrons, right? So this is how the reaction takes place at the 2 different electrodes. Overall equation, just to recap again, we need to first balance the electrons, right? So now the electrons are not balanced, so what I need to do is that I need to multiply the cathode one by 2, right? So this will give me 4OH minus plus 4 electron plus 4H plus, later then I'll put back the state symbol, give you 2H2O plus O2 plus 4E plus 2H2. Cancel out the electrons now, that's been repeated, and combine everything together, and you will realize that you actually started off over here with 4 of the H2O in liquid, it became 2 of the H2O in liquid, it became O2 gas, it became 2H2 gas. But then it's also weird to have your water appearing on left and right hand side, so we can also cancel out the water, 2 sets here, and then there'll be 2 sets over here. So overall the final answer, which is in my pink highlighted area now, will just be represented as 2H2O liquid gets electrolyzed to form 2H2 gas plus O2 gas. And this is why you realize that the volume of hydrogen collected will be twice the volume of oxygen obtained. So it's a 2:1 ratio, because the equation you can see is a 2:1 ratio. Right, so that is actually how the electrolysis of water works. Now in terms of part A, why water by itself is a poor conductor of electricity, I hope you remember in Sec 3, we learned that H2O, given that it's made out of a non-matter, is actually a simple covalent substance, right? And when it's a simple covalent substance, we know that it does not have any free moving electrons to act as charge carrier, or mobile electrons to act as charge carrier to conduct electricity. So this is what we learned in Sec 3, in case you have already forgotten. Okay, but we know that in the case of this whole chapter, we just learned that water actually is made out of OH minus as well as H plus ions, so that still allows some form of reaction to happen. Right, so what do you do with these boxes over there, in case you're wondering in the previous few pages what is expected for you to write over here? I would like you to really consolidate your things and then write the equation here again, right, in terms of what is happening at the electrodes that you are looking at. Right, so over here for the anode, this is what is happening, at the cathode, this is what is happening, then so on and so forth with the overall equation that you have at the end. Right, this will train you to get better and better at writing ionic equation, to get better and better at learning how to combine equations together to form an overall reaction. Okay, so after this part of the video, I would like you to take a look at the instructions from your teachers to try out some questions on your 10 series first, and before you move on to part 3 of this entire chapter, which is the very final part of electrochemistry. That's all for this video.